Welcome back. Now we have this ability to perform a box trace. So we have a few things going on here. We have a box component on our sword, which we can see if we show collision. It's right there around the blade. Now we're triggering overlap events with that box component. And as soon as we get an overlap event, we want to get a more accurate vector representing the hit point. So we perform a box trace down the blade, and as soon as we hit something with that trace, then we get a hit result, and we're showing a debug sphere at that hit location. And so this gives us a bit more accurate of a location for our hit. Now, we're doing all this in Blueprint in our BP weapon class, and we'd like to learn how to do all this from C++. Now, because there are a few moving parts to this, we'll take this one step at a time. And the first thing I'd like to point out is that on our weapon box, our box collision, we set our collision response to the pawn object type to ignore. And that way we would avoid getting an overlap event for our box component on the capsule. Now, the mesh itself was set to pawn for its object type. So we selected that character mesh right here on this instance of /character in the world, and we changed its collision presets so that its mesh has the world dynamic object type. And we made sure that this mesh is set to block the visibility channel. So it's important to understand the collision presets for the things we're interacting with in the world, and also the responses for things like our collision volumes, like our box component. So we've set these from the blueprint, but these can also be set from C++, and we're going to make sure that we configure this properly in our weapon C++ class. So let's hop back over to our / project and go into weapon.cpp, where we're actually creating our weapon box and setting it to be attached to the root component. Now, we can set the collision presets settings from here in C++ with a few handy functions. We have to access the weapon box, and there exist a number of functions for setting the collision presets. For one, if we wanted to make sure that the collision enabled is set to query only, for example, we would use set collision enabled, which takes an enum of type eCollision enabled. And of course, we've seen that we can set this to no collision, physics only, query and physics, or query only. So it's set to query only by default. That's kind of what box components get as their default, but we can set it here just to make it clear that we definitely want our collision enabled set to this setting. Now, we can set collision responses to various types. And if we look in blueprints, we'll see that we have overlap set as our response to all collision types except for pawn. Now, say we'd like to hard code this into C++ to make sure that our C++ class reflects our intentions here. And we can do that. We can take our weapon box and set its collision responses. Now, there are a couple of functions. One is set collision response to all channels. And this takes a collision response, which is an enum of type eCollision response. So these types are all enums here in C++. And we can choose overlap. And what this would do essentially is check all those checkboxes here in the collision presets to overlap for everything, including the pawn. That's what this line does. But after setting the response to all channels, we could then set collision responses to a single channel. So to do that, we take our weapon box and we call set collision response to channel. Now, this function requires that we specify the channel. So we have an eCollision channel and an eCollision response. Now, we can type eCollision channel with the double colons, and we see all the channels here. So we see camera, destructible, we should see pawn down in there, and in addition to that, there are more enum constants in this enum. Those are reserved for custom channels that we can create. But we're going to choose pawn here, and we're going to choose to ignore the pawn. So we're going to type eCollision response for the response input, and this is going to be ignore. So first, we're setting the collision response to all channels to overlap, and then we're specifically singling out the pawn channel and choosing to ignore that collision channel. So that's how we set this from C++ here. Now back to the blueprint. In our event graph, we're taking our onComponentBegin overlap event and performing a box trace. Now that we have this weapon box, we're going to want to respond to overlap events in C++. So we'll need a couple of overlap functions on the weapon class. We have overlap functions for the sphere, but now we have a box. So let's go ahead and make those overlap functions for our weapon box. And we'll put them just under our sphere overlap functions. And they're going to take the same input parameters. So we can declare these functions. We could make them virtual if we want to. But what I'm going to do is leave them as non-virtual. And if we make a child class of the weapon and decide to override it, we'll make it virtual then. So I'm going to call this on box overlap. And we need the same input parameters as we plan on binding this to the onComponentBegin overlap delegate on our weapon box. So I'm going to paste in those input parameters for onBox overlap. So we do want a function for when our box overlaps with something. We're not particularly concerned right now about end overlap, so I'm only going to make onBox overlap, not an onBox end overlap. And of course, this is going to be bound to a dynamic multicast delegate, which means it needs to be a U function. Remember, onSphere overlap and onSphere end overlap are U functions. We just have that macro in the parent class that we're inheriting these from, which is item. See here in item.h, we have the U functions there. So if you override a virtual function that's a U function, you leave that U function out because it's inherited from the parent version. But onBox overlap is not an override. It's an original function declared here in weapon, so it needs U function. So let's make a function definition for onBox overlap. So we have it here, and we also need to bind this to the box components onComponentBegin overlap, and BeginPlay is the place to do that. Now, we don't have a BeginPlay here. Our weapon.h was not given a BeginPlay. In fact, it started out completely empty. So we want a BeginPlay function. And if we take a look at one of our other classes that does have BeginPlay, such as our character class, we can scroll up and see that BeginPlay is a protected function. So we're going to want to override it here in weapon.h in the protected section. And I'd like BeginPlay to be the first protected function here. So this is a virtual override. So we'll say virtual void BeginPlay override. And we'll go ahead and implement BeginPlay. So here's my BeginPlay. I'm going to highlight it and Control X to cut it and move it up towards the top, just below my constructor. I'd like to have it there. And because we're overriding BeginPlay, we need to call super BeginPlay. Very important. And after we've called super, we can bind our callback to our box components delegate. So we're going to take our weapon box and access onComponentBegin overlap and use add dynamic. And I'm going to click so I don't get that internal add dynamic. Now, the user object is this, and the callback function is going to be the address of a weapon on box overlap. So now my function should be bound. We should get that callback in response to an overlap event on the box component. And then we can go about actually doing our box trace that we were doing in Blueprint. Now here in Blueprint, we have a start and an end scene component. Now we added these here in Blueprint. We want to add them in C++ instead. So really we can delete these here. I'm going to go ahead and just remove all these nodes as we're going to do this in C++ now. So I'm going to delete the end, I'm going to delete the start, and we're going to add those scene components from the C++ class. So back to slash into weapon.h, we can make a couple new scene component variables. And we'll do that down here in the private section. So I'm going to make a uSceneComponent pointer called start. and a useSceneComponent pointer called end. And to be more specific, start and end are kind of generic. I'm going to call this actually box trace start. And I'm going to call this one box trace end. That way it's very clear what these are really supposed to be. And these should be uProperties, and we'd like to be able to move them around in the editor. So this will be uProperty, and I'll make it visible anywhere. And I'll go ahead and give box trace end visible anywhere as well. So just like our weapon box, we should be able to access and change its properties. I know it sounds like edit anywhere would be more appropriate, but edit anywhere is more for individual variables that you'd like to be able to set and change, whereas visible anywhere is more appropriate when it comes to these components, as we can see the details panel and we'll be able to change any properties that exist on this class that are edit anywhere. So just a little nuance. Visible anywhere is typically what we use for components, whereas regular base type variables will get edit anywhere if we want to actually change them. Now, box trace start and box trace end are empty pointers. We need to actually construct these, and we'll go to weapon.cpp in the constructor to do so. So we're going to first start with box trace start and use create default subobject, specifying the type, which is useSceneComponent. And we can give this some display text. We'll have this say box trace start, and we'll attach this to the root component. So we'll take box trace start, setup attachment, passing in the root component that we'll access from get root component. And it looks like I have a typo. It should be box trace start. Now we'll do the same thing for box trace end. So box trace end, and we can simply copy this line, but we do have to fix the display text. It'll say box trace end here, and we'll go ahead and call setup attachment. So I'll copy that line and replace box trace start with box trace end. So here we're creating our two scene components. Now I'd like to save all and jump back into the editor and compile here, just so we can see those scene components and move them to the correct locations on the weapon. All right, so we'll go back to the weapon in the viewport. Here are our new scene components. I'm going to select box trace start and make sure that it's down at the bottom of the blade. So we'll stick it down here, and we'll go up and select box trace end and stick it up here. So now our two scene components have their correct locations set. So I'm going to save that, and we'll hop back into C++. Now we're ready to actually perform our box trace. So we'll do that in our overlap function called onBoxOverlap. Now we have two scene components, right? These are scene components which each have their own location. And I'd like to create a couple of variables just for convenience that will store those locations. So I'll make first a const f vector called start. And this will be the location of our first scene component, box trace start. So this will be box trace start. And to get its world location, it's actually get component location in C++. So in Blueprint, it was get world location. In C++, it's get component location. And that's a global space rotation in world space, not local space. If we took box trace start and called get relative location, then we'd have a local rotation. But we want world space. So we have get component location here. And I'll go ahead and make a const f vector called end. And this will be the box trace end. And we'll call get component location. So I know I had named the scene components start and end, and then I said those are bad names. But here in the overlap function, we'll be actually performing the box trace. So start and end actually means something right here, as we're just about to perform an actual box trace. Now, if we hop back into Unreal Engine documentation and search for box trace by channel, Then here is box trace by channel, but of course it's showing us the blueprint version. But it also says here, target is Kismet System Library. That seems to indicate that this function exists in this particular library. And Kismet System Library is kind of like Gameplay Statics. It's a static function library, and like Gameplay Statics, it's a class that begins with a U. So let's see what happens if we search for U Kismet System Library box trace by channel. So the fully qualified function. And take a look at this. We have Kismet System Library, and it's showing us sphere trace. So it's like, is this what you mean? And we're like, no, we want the Kismet System Library box trace function, but it shows us here's U Kismet System Library, and here we have a list of all the functions here. So we can actually search for box trace here. So let's search for box trace, see if it has anything here. And of course it does. It has box trace multi. Now, multi means we're sweeping against multiple objects, and it says sweeps a box along the given line and returns all hits encountered. So that's if we want multiple hits. Let's continue our search. We have multi by profile, multi for objects, box trace single. Hey, wait, this sounds like what we want. Sweeps a box along the given line and returns the first blocking hit encountered. That sounds a lot like what we want. And we can trace by profile, we can trace for objects. Now, if you're wondering what profile means, profile is one of those things in the collision presets. If I go back and take a look at my weapon box and go into my collision section, right here where it says collision presets, these are profiles. So you can sweep or overlap checking against those as well. Now, I'd like to do a box trace single, which simply sweeps against a particular collision channel. And we can use something like visibility. Now, this function exists in Kismet System Library, but if we click on box trace single, we'll be taken to its documentation page and shown the include for Kismet System Library. Surprise, it's in Kismet/Kismet System Library. So we can copy that, and back in weapon.cpp, we can paste that include right there at the top. And now we can trace with a box trace right here. And we do that by accessing U Kismet System Library. And this being a static function means we can call the function on the class itself. So let's start typing box trace single, and there it is, box trace single. And if we start with the opening parentheses, we get our pop-up telling us all the inputs we need, and we see that the last few have default values. That's how these default values work. They're always the last inputs for a function. You can't have an input parameter with a default value and then the next input not have a default value. As soon as a function has a default value, then all other input parameters that come after it have to have default values. That's how they work in C++. So anyway, we have box trace single. And being a static function, it needs to know the world we're in. Therefore, it takes a world context object. Well, most of the time we can pass in this as the world context object, as this is an object in our world. Now notice I hit enter and put this on the next line. You can do that to make your function calls a little neater if you want to see all the input parameters without them running off the screen like this. So I'm doing this for your convenience as you're watching this on a screen and you want to see all the inputs. So after the world context object, box trace single takes a start and an end. So in the previous video, we mentioned that these traces need a start and end point. Well, we happen to have those. So for the start, we'll pass in start. For the end, we'll pass in end. It's that simple. Now, next we have the half size for the box. And I'd like to give myself a little bit of leeway for this box. I don't want it to be too large, but I want to make sure I do hit things. So I'll give this an F vector. This has to be a vector, and it needs the half size in 3 dimensions. I'm going to give it 5.f in all 3 dimensions. So 5.f for x, 5.f for the y, and 5.f for the z. Now it also needs an orientation, and you know what? We can use the same orientation as our box trace start. So really I could take box trace start and I can call get component rotation. And that returns an F rotator for me. Now the next input parameter says eTraceType query. So it's an enum of this type, and if we type eTraceType query, and we right-click on it and peek its definition, we'll see the traceType query enum here. And it's in enginetypes.h, and the comment says, specifies custom collision trace types overwritable per game. And the enum constants aren't very descriptive, they just have traceType query 1 through 32. Now, it doesn't really matter what we put here. Box trace single is basically tracing against the visibility channel. If we wanted to set up custom trace type queries, we could in the engine and pass in the number corresponding to our custom type, but we're not doing that, so we're just going to pass in the first enum constant to satisfy that. And after this input, we have a Boolean called bTraceComplex. Now, to understand this input, we have to remember that our skeletal meshes have a physics asset. That's those capsules we see whenever we show collision. And static meshes have collision hulls, which are basic geometry that we can see if we open them in the static mesh editor and show simple collision. And those are what we would trace against unless we set this Boolean bTraceComplex to true, in which case we would trace against the actual geometry in the skeletal mesh or the static mesh that we hit. And that's much more expensive. So we're not going to use trace complex. We're going to set that to false. Now next we have a const t-array of actor pointers. Now don't worry about this default allocator. That's a setting specified in the input parameter, but this input parameter can accept a t-array of actors. And it's called actors to ignore. So we can make a t-array of actor pointers and add actors that we would like this box trace to ignore. So we won't actually get a hit if it hits one of those boxes. So since we need to pass one of these in, we can create one. We can make a t-array of a actor pointers. And we can call this actors to ignore. Now, I believe this is the first time we're encountering t-arrays. So what exactly is a t-array? Well, it's a container. It's an array, so if you've created an array in regular C++, that's what it is, but this is actually a class that contains an array inside of it. And this class is built with the functionality such that it can dynamically expand the size of the array as it needs to. So it has an array inside of it of fixed size, but each time we add an element to the array, if we fill that array up, then it'll do some magic internally to create a new array of larger size and transfer all the contents into that. So this class contains a regular C++ array inside of it, but it has the ability to dynamically increase the size of that array. So the implementation details are not something we have to worry ourselves with right now. We just have to understand that this container can store multiple values of the type we specify in the angle brackets here, as this is a template class. Now we know about template functions. Template classes are very much like template functions in that they can take a type as a parameter, and the t-array, for example, can store multiple objects of that type. Now, whatever we add to this actors to ignore array, once we pass into box trace single, those will be ignored by the box trace. And to add something to this array, we take the array, it's called actors to ignore, and we use the add function. Now, we don't typically make pointers to t-arrays, we just make a t-array. So that's why I'm not using the arrow here, I'm using the dot operator. And add can take in an actor pointer. For example, if we want our box trace to ignore the weapon itself, we would pass in this. And now we've added a pointer to the weapon itself to actors to ignore. So this will make sure that we don't actually get a hit on the weapon itself. And we can pass in actors to ignore as an input parameter. That's why this function takes an array of actors. So we'll pass in actors to ignore. Now the next input is another enum called eDrawDebugTrace. Draw debug means we can see the debug boxes generated by this box trace, just like we did with the blueprint version. So we can specify eDrawDebugTrace and see our options. We can draw it for a duration. For a single frame, we would use this if we were tracing every frame in tick, for example, or none for no debug, or persistent if we want that debug box to stick around. We're going to use for duration. That way we'll see it for a few seconds and it'll go away. Now after this draw debug trace, we have the f hit result. This is the hit result. And if you're confused because the blueprint node had this as an output, this one takes it as an input, well, this is how some of these functions in Unreal Engine behave. They'll take an f hit result as an input and fill in the variables of that hit result. So it's taken in as a reference. And when you have a function that has an input parameter of reference type, then if that function changes any properties on that object passed in, those changes will stay. So what we can do is create a local variable of type fHitResult. And we can call this box hit. So we've just created a brand new box hit, which is an fHitResult. We see that it's a struct. And if we pass this in, box hit, it's being passed in by reference. And in fact, Unreal Engine will sometimes name the input parameters with out in the name. So this one is called outHit, and that means it's an out parameter. So box trace single will fill this in with information, and after we call box trace single, our box hit result will be populated with data about that box trace hit. So a good indicator that something is an out parameter is if it's passed in by reference and it's not a const reference. If it were a const fHitResult reference, then this function would not be allowed to change it. But it's a non-const reference, so box trace single can change it, and it indeed will. Now, next is a Boolean called bIgnoreSelf. If we pass in true for this, well, then we're ignoring ourselves, which is kind of the effect that we achieved by adding this to actors to ignore. So that's kind of redundant, but at the same time, it's a required parameter, so we're going to pass in true. And the rest of the inputs have default values. The trace color can be red, just like we saw in blueprints. The trace hit color can be green, so as soon as that box trace hits something, we'll see green. And then we have a draw time of 5 seconds, and I'm okay with 5 seconds. So we'll leave the rest of those inputs as is. And now we're performing a box trace, and after all that hard work, we can go ahead and save and hop back into the editor and hot reload and try this out. So after a hot reload, we'll go ahead and press play, we'll grab a weapon, we'll run up to this other character, and there's our debug for the box trace. Everything is looking great, and notice something. As soon as we get a hit, not only do we see a red box and a green box for where we got the hit, but we also see a red point. Remember when we drew debug points? Well, there's a point indicating exactly where that impact happened. And that is where we would get the location of the impact point from our hit result. So this is working, everything looks great. And before we wrap up, I'd like to revisit the fHitResult just a little bit, just so we understand what we got here. So I can right-click on fHitResult and peek the definition, and I'm taken back to engine types where it's defined. Now, don't worry about the red squiggles. Sometimes IntelliSense can take a little while to catch up, but the fHitResult has a number of variables, and I just want to point this out that you can browse to this particular file and see that each of these variables have extensive comments here. Basically, these are the comments you would find in the documentation, and you can come in here and read these and see exactly what they are. And you can notice that the location and the impact point are F-vector net quantizes, which behave just like F-vectors. In fact,
FVectorNet Quantize is a child class of the FVector type, so you can do everything to these that you would do to FVectors. The only difference is they're optimized for network replication, which is not something we need to get into right now. But I want you to know that these comments will tell you in detail what each of the variables on the fHit result are. But for now, all we're concerned with is using that hit result to see what we hit and see the impact point of our box trace hit. So this is great. We now have a box trace that we're performing in C++. We've done it in Blueprints, now we know C++, and we're ready to continue using this in our game so that we can actually start doing things to the actors we hit, such as destroying them, killing them, breaking them, whatever we want to happen when we hit something with our sword. So great job. I'll see you in the next video.